Good evening, Tony Peters with another quick update. Just getting everything back to the way it was before the hurricane hit. So bear with me. It's actually starting to look like an actual test setup in here. So a couple different things to talk about. Right now I'm just having, move this out of the way for a minute. This is just my test cell, my 6-volt, 1-watt test solar panel. It goes to a 3.5 millimeter housing there. So I had a couple different things pop up as I was experimenting, using some new parts. As I talked about before, I was trying to, for the beta angle position and control subsystem, I was toying with the idea of going from just a potentiometer and a servo to the 28 BYJ stepper motor for more precise angle measurements. I've demonstrated that before. Moving to the NEMA 17 stepper motor, so I get that fidelity of 5.625 degree per step, now is at 1.8 degree per step, and I could set up in microstep mode and I get 1600 steps per revolution. And again, I could start using some creative code to get some really fine-tuned accuracy in here. I'm still troubleshooting some of the issues. I had a driver burnout on me. Just little things like that have been happening, and some of these parts are kind of long lead. I can't get a lot of them on Amazon next day, unfortunately. So this is the NEMA 17. I got a couple different things on here. Usually you just get this one little piece here, but I got a nice little professional looking mount with it, two-way, and then I got a 5 millimeter housing that I'm working on to try to use and mild this together. Just something basic, just some lightweight aluminum that I can use this to rotate, and then have my artificial sun module subsystem kind of rotate over the cell like this. So of course I would have it lined up. This is my thermal base plate, my honeycomb substrate. So as I was monkeying around with some things, especially with these really fragile solar cells, I have here, like I said, this is below a single junction in terms of performance, but I also have this really nice, courtesy of Spectralab out in California, very expensive, but it's a gallium arsenide triple junction solar cell. I'm going to do some testing with it. I have an entire binder to accompany this, but this is very fragile, and I kind of want to do some things to preserve the cells before, because some people might start operating this test setup and might not know exactly what's going on. So I got an idea when I was going to use these SR04 ultrasonic sensors. I'll give you a little close-up view of them. They're great up to about 2,000, 3,000 millimeters plus. Very accurate. You can have them set up that way and programmed, do some basic maths in order to get you that calculation in millimeters, which I'll demonstrate here in a second, what it actually looks like. However, as you can tell, there's quite a large cone of sensitivity here. I'll talk about a little bit later in my PowerPoint and mention. So I was going to use this as it rotates above the cell to kind of give you some accurate distance measurements. Well, turns out because of that cone, I can have it oriented this way or this way. Once it passes about 45 degrees, you start to get some really erroneous data, obviously, and then when it gets too close to something, you get that cone of sensitivity when it's less than about 20 millimeters. So it's really not going to perform the way I want it to. Therefore, I came up with a couple different things here I want to talk about. So this is the VL6180X time of flight distance sensor. It actually has a lux sensor co-located on it over MIA. And originally you're supposed to use two sensors, one sends, one receives, but I'm trying to work with this and a different type of sensor, the V51LOX, which is something I'm trying to do a simulated LiDAR, light detection and ranging setup. Obviously this takes up less power, it saves up way more space, it's lighter weight, so putting it on top of this structure where I'm moving it over top of a cell would definitely save me some real estate there, so I can add a couple of other things. This would be my UV sensor. I've already started working on some of the code on this one to give me some data in milliwatt per centimeter squared. to measure UV. This is the MCP9808 that I've been talking about previously in other videos, which is my very high accuracy temperature sensor. A couple different thermocouples or thermistors in here to do some fast calculations and give me very good readings. I was thinking about using that at the top of my ASMS, and then having another temperature sensor, which would be a contactless temperature sensor, and it emits a signal kind of like they use in the medical industry. I got the idea from my wife when she was snapping different parts of someone's body, and it was giving her very accurate real-time temperature measurements. I thought it'd be really interesting to use as a contactless method for looking at the surface temperature of the PV cell, which you can look at the environment that it's in. You can have a thermal base plate temperature, and you can also get real-time data for the surface of the cell, which is actually the part that gets the hottest. Actually, it's the bypass diode that gets the hottest, but a lot of these don't have bypass diodes. So you can actually aim it at exactly whatever part of the cell you want, and I mount that on top of the ASMS. Another good thing that I've gotten to save space is I've successfully put this whole thing together here. Actually, not much was really required to put it together, but I've managed to get a smaller version of the Metro 328 microprocessor. It's a little hard to tell exactly what's going on here, but micro USB compatible, and you sacrifice quite a few digital inputs, but I think it'll work very, very well. I've been able to integrate it here into my proximity warning system. So without taking too much time, I've also been able to save more space through what's called an LCD shield. So it takes all 16 inputs and translates that into ground voltage and a data and a clock. As you can see here, it might be a little difficult to tell, but all four of these, and it saves a ton of cabling and harnessing required that I did not have before, or I didn't have the libraries for compiling in I2C COM protocol previously, but I'm going to start doing this from now on. It'll save a lot of space, and like the 20x4 LCD here, I actually have it already soldered on. The potentiometer's on the back, but I can basically just twist it all the way to the front and then give it a crack out, save a little bit of power there. On downside is I don't have a potentiometer on the outside to kind of dim or turn off the display. You're kind of sacrificing that, but a lot less cabling involved, and I don't have to make my own circuit using these PCBs and solder everything together. So I got this whole thing set up over here. So as I was saying, as things are moving over top of this thermal base plate and over these really fragile cells, I think it'd be pertinent to have a proximity warning system, and I can manage my thresholds. But right now, I think that 25 millimeters is a good start. I might make it increase depending on when I finally put everything together on my hardware. And let me just fire this up, and you can kind of tell exactly what's going on. So right now I'm getting all these sorts of weird readings for the distance to this cell, but as I come closer and closer to it, I have it programmed to light up a red LED, get your attention there, but a red LED is probably not going to get your attention, so I put a piezo buzzer there, which just uses an analog or a digital pin input from one of my digital pins here. I'm not taking up too many because now I have an LCD shield, so I can use a smaller microcontroller. And I was thinking about positioning them in critical positions along the path or the trajectory of the ASMS arm that's moving over this cell. So if it gets too close to the edge of a setup, and you can move them around, I think it'd be really good to have as a safety measure, because some of these cells, my triple junction cell alone is about $350. So that's something, versus this is 20 bucks, and it's pretty resilient. You could take it outside with you, but not all cells are like that. So you need to take those kinds of considerations, I think, for an experimental lab where you may have graduate students or professors showing undergrads how to do it, or other people. And I think when someone sees a red light go off and a giant buzzer, it'd probably stop them dead in their tracks. Be like, oh, I probably should give it a second. And then they go to the LCD and it says, stop moving everything. I was also thinking of installing some kill switches that are directly linked to the NEMA 17 stepper, so that once you're taking the rotary encoder and turning it to a specific position, it'll have a no greater than or no do not exceed value. And then if it even goes past that, it'll hit a kill switch or a limit switch that works well with steppers, and it completely cuts off the motion. Using a release command, when I program that into the code, it actually allows the servo or the stepper motor to freewheel, which means it'll become a brushless, frictionless shaft at that point. It'll go to its resting position, to whatever position I have. So think about using some hard stops from 0 to 180 degrees, maybe a little bit more than that. But I think that's probably a good place to start. As you can see, certain things are starting to come together, but as this thing evolves, some other concerns start to come up. So I'd like to cover them now in the experimental test phase before I get too far down the line and be like, man, it would be really great to have this. So with that being said, a couple other systems I'm working on right now, but I wanted to at least show you this one little nifty thing that I had kind of put together. Hopefully it all pans out, and I'm looking to try to have some serious headway made on the BAPSIS, working with this NEMA 17, programming it to the rotary encoder successfully, but I'm waiting on my one driver assembly to still get here. So as always, any questions, please feel free to send me an email. Thank you.